record. Okay, so in the last session, we had started discussions on asymptotic complexities, right? Complexity analysis, analysis of algorithms. And we defined a couple of notations called asymptotic notations, 5 of these. And we used 2 approaches. One was based on sets, set definition, and another was based on limits, right? And here in the set notation, so 2 students identified, so majorly 1 student identified a bug in the definition, right? So the bug was this: for small o and small omega, it's not there exists C. So the definition should be changed to for all C greater than 0, right? Now, when you compare C and 2C, there does not exist, that means for all C, this is not correct, right? So if you compare n and 2n, this is not correct. For example, if you consider C is equal to 0.1, this does not work, right? Okay, so now with this fixed definition, let's clear all drawings. Let's move on. So we scanned how to use both these set definitions as well as limit definitions to solve a couple of problems, right? And we also looked at how to analyze the complexities of kernels. So those were just 2 loops, but you can expand it to more complicated structures, 3-line code with conditionals and with a lot more complicated mathematical expressions, right? Okay, and here we said that in the limit definition for small o and small omega, so we have equivalent relationship between limits as well as this definition, right? F of n belongs to O or omega. But for theta, you should be careful. If a limit exists, that implies a theta relationship. But if 2 functions are related by theta, then it does not mean that there exists a limit, right? So you should be careful here. Okay, and we covered all these, and see, this gives you a lot of problems. You can try to prove each and every particular relation here using the set notation. So try to solve, try to give proofs for each and every relation here. Okay, so these are a lot of examples we covered. Let's start from this. Is it true that given any 2 functions, there should be at least one of these 5 relations that has to hold between the 2 functions? That's not true. So what is the meaning of between any 2 functions, at least one of the 5 relations has to hold? So that means the relationship between every 2 functions are covered by these 5 relations. That is not true. So here is a counterexample. See, if you consider f of n is equal to n and g of n is equal to a conditional like this. If n is odd, it is 1. If n is even, it is n squared. Now, can you tell me what is the relationship between f and g? Is f smaller than g?
Not determined.
Right, so you cannot determine it because in some cases it is smaller, in some cases it is larger, right? Hence, we cannot have any of these relations between f and g. Okay. Next. Okay, so consider any 2 functions, f and g. See, whenever we discuss functions here, we assume they are asymptotically positive, right? We defined what is asymptotically positive, and we said that from now on, whenever we consider a function, they are automatically asymptotically positive. Okay. Okay, given two functions, f of n asymptotically equals g of n, if and only if, IFF means if and only if f of n is asymptotically less than or equal to g of n. Okay, from now onwards, I will just say less than or equal to, greater than or equal to save time. Okay, f of n is greater than or equal to g of n, right? So how should we prove this? So whenever you see if and only if and only if, that is A, prove that A, if and only if B. Then there are two parts. If A, then prove B. If B, then prove A, right? Part one, part two. So we have two parts here as well, right? So if f is equal to g of n, then f is less than or equal to g of n, and f is greater than or equal to g of n. Part two, if fn is less than or equal to g of n, and f of n is greater than or equal to g of n, that implies f of n is equal to g of n. Okay, asymptotic. The proofs here are very simple. We will use set notations, right? Set definitions. When you use set definition, what is the definition of f is equal to g? There exists C1 and C2, both positive, such that, and there exists n naught, a natural number n naught, such that for all n greater than or equal to n naught, f is in between the C1g and C2g, right? That's the definition, right? So this automatically implies, just consider this. And then consider f of n, C2, the relationship between f and C2 g of n, right? So you're just breaking this relationship into two tiny relationships. But you see that the first line is f of n greater than or equal to g of n. The second line is f is less than or equal to g, right? So similarly, you can prove the other part as well, right? It's going in the reverse direction and it works. Okay, simple proof. Now, let's consider a very important identity. So you might have to use this in a lot of places. See, whenever you see a problem like 2 power n plus n squared plus 1.5 power n. What is the complexity? O of what? What is the final answer?
2n, 2 to the power
2
of
power n.
Right? The smaller terms do not matter. Right? That's exactly what we will use here. Okay, see the max of 2 power n squared 1.5 power n is just 2 power n. Okay, so how can we prove this? You can also try using set definition, but here we will use limit definition and it will be very easy. Okay, so if we want to use limit definition, so how should we prove? I mean, think about it. So whenever we have equal to, right, that is theta, that's the theta notation. If limit exists, then if limit exists and it is non-zero, right, it is a non-zero constant, then it is a theta relationship, right? That's what we will use here. Okay, now let's consider this f of n plus g of n as one function, and so just a minute. I have a class.
Because the recitation, I don't know the passcode for the recitation.
Oh, so
Yeah.
okay, just a minute.
Yeah, because the recitation is going to start soon.
Now, can you talk to the other keys? F of n plus g of n, right? This is one function, and max of f of n comma g of n. This is the other function that we are comparing here, right? So you can consider this summation itself as one function. Max is another function. Okay, we are comparing the relationship between these two. So let's take one over the other. Okay, so what can we do now? We will find the upper bound and the lower bound of this ratio. Okay, so to see the upper and lower bounds, now consider max of f of n comma g of n. So it is either f or g, right? Without loss of generality, let's assume it is f. I mean, if you want, you can use case 1 and case 2. Case 1 is when max is f, case 2 is when max is g, right? Okay, without loss of generality, let's assume it is f. Okay, that means f of n is equal to f of n, g of n less than or equal to f of n. That's the meaning, right? Then f of n plus g of n is less than or equal to f of n plus f of n. That is 2f of n, correct? Right? It's upper bounded by 2f of n. What is the lower bound? I mean, you can cancel this g of n out. The lower bound is f of n, right? So this is greater than or equal to f of n. Okay, now consider this max of f of n comma g of n. You know that it is f of n. I mean, that's what we assumed here without loss of generality. Let's use that f of n in the denominator, right? We are using that in the denominator. What do you get? 2f divided by f, here 1f divided by f, 1 and 2. These are the lower and upper bounds, right? So these are the lower and upper bounds. Hence, this is a non-zero constant. This is a non-zero constant. So if it is a non-zero constant, what's the meaning? If the limit is a non-zero constant, it is a theta relationship, right? The two functions are asymptotically equal. Done. Simple, right? Okay, now here we have used the limit definition. Can you try using the set definition and prove the same result? So in fact, many of these theorems, whatever we have, right, you can try to solve using both the set approach as well as the limit approach. And you will see that for some cases, the limit approach is very simple. In some cases, the set approach is very simple. So you should try to think about, which classes of problems are ideally suited for limit approach and which classes of problems are ideally suited for set approach. And it's not very clear, right? With some practice, or you can try both approaches and choose one, right? Whichever solves the problem very easily. Okay. Next. Okay, suppose you have two functions, f and g. Now let's take the difference of f and g. Suppose we get f minus d, and that is asymptotically positive. Now, can we say that max of f and g is asymptotically equal to f minus g? This seems like a very nice problem, right? See, if you analyze something like this, f of n is say n cube minus g of n is say n, that is theta of n cube, max of n cube and n. We got the result here, right? So maybe f minus g is asymptotically equal to what? F. If f minus g is asymptotically positive, right? That's the claim. but we will disprove it. See, this is not true for all functions. So here is one example. So I mean, this was a simple example. Suppose you assume that the first term cancels out, right? So here the first term is the dominating factor. Suppose that cancels out. What happens? F is n squared plus n and g is n squared plus 1, and they cancel out. When they cancel out, what do you get? A max of f and g is really n squared, right? Max of f and g is really n squared. However, f minus g is now n, right? So here it's asymptotics. I'm writing the asymptotics. And they are not equal. So this is not true. Okay. So for any false statement, you just need to give one example. That's the counter example. And here you cannot give reasons and all. You need to show a counter example. Only using a counter example, you need to disprove. I mean, something like this. I mean, not always. I mean, there are some very beautiful statements for which the only known examples or known proofs are using contradiction, right? Using contradiction, you can disprove it. They don't know any counter examples, but using contradiction, they can disprove it. But most of the problems we will see, if you say the claim is incorrect, you should give a counter example, right? And okay, think about this. The first example you try here, n cubed minus n squared is equal to n. Sorry, n cubed works out, right? That matches with whatever has been claimed. So you should not try the first example. Just because this work, it doesn't mean the formula is true. One example cannot prove a universal statement. A trillion examples cannot prove a universal statement, right? A Google examples cannot prove a universal statement. But one example can disprove a universal statement, and that's the counter example. Okay? So just because you got a working example does not prove the claim. Okay, so here if you want to prove it, you have to prove it rigorously. If you want to disprove it, just give one example, you're done, right? Okay, next. Suppose you consider two functions, f of n and g of n, right? If f is equal to g, then f power k is equal to g power k, and vice versa for any positive k. So I'm not going to explain the proof. It's a very simple proof. Go over this, right? You just need to raise the entire equation to the power k, and you can do that, right? From the laws of algebra, if a less than b, assume that a and b are positives. Can we say that a power k is less than b power k? Right? So, okay, so check that. So let's move to another problem. This is a beautiful problem, very beautiful problem, and the most important problem. Why? Because this deals with polynomials, and almost all functions that we will touch upon, right? The programs we'll touch upon have polynomial complexities. We rarely work on exponential time complexities, right? For example, chess, Go, and all that. So most of the problems we work on have polynomial complexities, most, right? Okay, so we want to have some theorems related to polynomials. And this is a very generic polynomial, right? Okay, consider, I should have written this as T of n. T of n is a polynomial of degree k. right? T of n is equal to ak n power k plus so on, the remaining terms. So you know a polynomial. Here, ak should be greater than 0. Can you tell me why this has to be positive? ak, why this has to be positive? What if it is negative?
Then eventually Tn will be negative.
Right. So you want to make sure T of n is asymptotically positive, right? In the worst case, it has to be asymptotically positive, right? So we consider ak greater than 0. Then this will never be negative. Okay, so here you want to show that T of n equals n power k, asymptotically equals n power k. That is the largest degree, right? So this equal to theta of n power k. So how can we prove this? We can prove using both the approaches. Let's try both the approaches. First, we will try the set approach. Then we will try the limit approach. Okay, so whenever we have something like this, in the set approach, how does it work? You can have two parts. Show that T of n is less than or equal to n power k. Show that T of n is greater than or equal to n power k. So there are two parts, right? Okay, let's prove each of these two parts using the set approach. Okay, so you have this polynomial T of n. The first part is less than or equal to n power k. You have this polynomial T of n. What do you see here? ak is definitely less than or equal to absolute value of ak. ak minus 1 is definitely less than or equal to absolute value of ak minus 1. a1 is less than or equal to absolute value a1. a0 absolute value a. Right, just taking the absolute value and having a less than or equal to relationship. That's what we want, right? We want to write this in the form less than or equal to some constant times n power k. That's the definition of asymptotically less than or equal to. Okay, so this is a constant. You know, this is a constant. All the coefficients are constants. They are not some functions, right? So this is C2, and that's it. As per definition, we have proved it. What about greater than or equal to n power k? So why can't we just say ak n power k plus so on is greater than or equal to n power k? Isn't this obvious? This should be greater than or equal to n power k, right? Why do we have all this complicated proof? Isn't this obvious? I mean, just remove the other terms and remove this, done, right? So why can't we have this simple inequality?
Can AK be anything between 0 and 1? It can be, right?
Right, AK can be less than 1. When AK is less than 1, what happens? It doesn't work, right? So you need some other approaches to solve this problem, right? So here you're assuming 1. It's not necessary that you need to have 1. Right? What's the definition of this? For some constant c greater than 0, you want to show this is greater than or equal to that c times, say c1, c1 times n power k. Right? It need not be 1. So how do you show that? Right? So there is a very complicated proof here. I will not go over this. And you know, these kinds of proofs are not expected from you also, but I have just, you know, put it here so that you can understand for some problems using the set approach can be extremely complicated, right? So go over this. There are a lot of details. understand each and every term here. Why did we choose this and so on? And verify the correctness of this proof. If it is incorrect, right, let me. Okay, so this is the set approach. See, at least for this problem, the set approach is super complicated, right? Next, let's use the limit approach. So what is the problem here? Is there any problem here? Limit approach, is it very complicated? Let's see. So we have this polynomial, all the constraints are the same, ak greater than 0. Now we want to compare these two functions, this t of n and just n power k. So take the ratio t of n, n power k, n tends to infinity, right? So expand t of n divided by n power k. Now split the terms, it's the common denominator, right? So you can write it as the first term divided by n power k, second term divided by n power k, so on. And cancel out the terms related to n, powers of n. What do you get? Ak, n power k cancels. Ak divided by n, there is one extra n factor here. So on, a1 divided by n power k minus 1, a0 divided by n. What happens when n tends to infinity? All these will be 0, right? Because the denominators are zeros, the numerators are constants, and it does not matter whether they are positive constants or negative constants, they do not matter. They go to 0, right? At the limit, they go to 0. What about ak? If ak was less than 0, we have a problem, right? Or if ak is equal to 0, we have a problem. But we know that ak is definitely greater than 0, so the limit is ak, it's a constant, limit is ak, and ak is greater than 0, so the limit is a non-zero constant, a positive constant, of course, right? Hence, the limit exists and it is non-zero positive constant, hence the theta relationship. Simple, right? 2 lines, right? So again, this shows that in some cases, the limit approach is very easy. In some cases, the set approach is very easy. Okay, so maybe you need to try both, get the intuition of, whichever is easy and use that as the proof. So in most cases, you will see that limit approaches are way better, right, in solving problems. Okay, I will skip this. This is another a specific polynomial. So there we solve the generic polynomial. So if it is a specific polynomial like this, how do you solve that specific instance? Using both the approaches, the set approach, the first is a set approach, second is a limit approach. Next, determining complexities from pseudocodes. This is very simple. I mean, we will see some basic patterns. So sequence of statements, you have like this, suppose 3 statements or n number of them. So time for taken for the first statement, time taken for the second statement, you keep on adding all these times, right? That's the total time for this code segment. Okay, what is the time taken for this code segment? It is an if-else ladder. Okay, the max of time taken for B1, max of time taken for B2, right? And this B3. Suppose this is theta of n, that block 1, right, takes theta of n time. This takes, say, n power log 3 base 2, and B3 takes theta of log n. Now, you know that max of all this is n power log 3 base 2, right? So that is the, wait a minute. So I think I made a mistake. So, okay, suppose B1 takes this amount of time, B2 takes this amount of time, B3 takes this amount of time. Now, can you tell me what is the time taken for this entire if-else ladder? Anyone?
Is it theta of n, because that's the max?
Okay, let's say n power log 3 base 2 is greater than n, right?
So that would be, then that would be the answer.
Okay, so like what is the exact answer? Can you completely say that?
So you're saying that n power of log 3 is the max, right? So then the answer would be theta of n to the power of log 3.
Okay, this one, right?
If that's,
So I mean, we
if
know
that's,
that log 3 base 2 is definitely greater than 1. Right? We know this is greater than 1. So n power greater
okay.
than 1 should be, right? Okay. However, this is not theta. Can you tell me why?
That is not.
For the code segment, the complexity is not theta. The theta, I said, is the complexity for each of B1, B2, B3, but for the entire if-else ladder, it is not theta. Why?
Because it depends on what the condition is. The
Exactly.
n log 2 base 3 is the worst case, and the best case is log n.
Right. So this is just the worst case, right? It's not, it does not always take n power log 3 base 2. So you need to write it as O. O means the worst case, not greater than this number. I mean, this function. So though individually B1, suppose it takes theta of n, B2 takes theta of n power log 3 base 2, B3 takes theta of log n, but if else ladder complexity is not theta because it depends on the condition. Sometimes it can just take log n time, right? Sometimes it can take n power log 3. It is based on the condition. We don't know what is the condition. Only at runtime we might get to know the condition. But what you can, the way you can write is O of the worst case is this. And what else can you write? It is omega of minimum time taken is log n, correct? Maximum time taken by this if-else ladder is O of this. Got
I have
it?
a question.
Yes.
So obviously we don't know the condition, but to say the general, like the average complexity, could we sort of take like an average of the three cases?
No. We can only take the average, right? I mean, so we have discussed about average case complexity slightly, right? Only in certain cases like that. Not here. Not here. We cannot take the average.
Okay.
So
If you know
average,
the probability of condition 1, 2, 3, then you can do that, I believe.
probably you can say with probability this, the complexity is this, but here we don't consider the average case complexity like this, right?
So then does this case not have a theta definition, just O and omega?
Yes, there is no theta here,
Okay.
right? For if-else ladder like this, when you have varied complexities inside it, there is no theta. Now, I mean, see, I mean, if you consider f of n is equal to this 1 and n squared, if n is odd, if n is even, just consider this simple conditional, right? Can we write f as a theta?
No.
No. It derives from this. We cannot write, it is impossible to write f as theta. The only thing you can write, suppose it is log n. The only way you can write about f is omega of log n and f is O of n squared. And suppose there are 100 conditions like this. And suppose they are in the range, right? You can say it is in the range from log n to n squared. The way you have ranges for numbers, right? Range from 5 to 10. Now you have ranges of complexities. The minimum is this, the maximum taken is n squared. It doesn't mean it can take arbitrary any function inside this range, but it just says the minimum time taken is this, maximum time taken is this.
Professor, I remember days ago, we discussed a worst case, best case, average case for search tree, right? Remember that?
Right,
So
right.
in that case, the worst case, you did
Yeah,
not
so-
find anything.
Yeah. So I mean, what you can say here is the worst case of this if-else ladder code segment is theta of n power log 3 base 2. The worst case, got the meaning of this? Worst case is equal to theta. So you
Yeah.
already defined that in the worst case, only block 2 will be running. You can say worst case is theta, that's fine. But you cannot say time complexity of this entire code segment
Okay, got
is
it.
equal
got
to
it.
theta. Make sense?
Thanks.
Okay.
I
Next.
got another question.
Yes.
Should we count the condition 1 or condition 2, the if statement, as the running time as well?
Okay, repeat again.
Say the maximum is whatever time block 1 to B3. Should we count the condition, say the runtime of condition 1?
Oh, I see. Yeah, here I'm assuming that checking condition takes theta of 1 time,
Okay.
right? Or maybe you might have a very complicated condition, check whether the chessboard is in the right. That might take n squared itself for checking.
All right.
Whether the chessboard in the checkmate configuration or not. That condition might take more time. That's okay, right? Then you need to include that also. True, you're right.
I see.
Right? But here, I'm assuming the condition is like a very simple if A less than B, something like that, the constant time condition.
All right.
Okay, that's a very good condition, question as well. You need to take into consideration the time complexities of condition. So in that case, you can say time of condition 1, let's see, plus time of this, time of condition 1 plus condition 2. Oh, wait, is it condition 1? No, so condition 2. Wait a minute. Condition 1 plus 2, correct. 1 plus 2, B2, right? Then time of condition 1 plus condition 2 plus condition 3, then B3. Make sense?
Yeah.
If you had another condition here, else no. Right?
Okay, thank you.
Okay.
Professor,
Yes.
you said that the worst case is theta of n raised to log of n,
Right.
but the time complexity is different. Can you explain the difference between the two?
So whenever you say something like time complexity of an algorithm, it includes all possible cases. For example, time complexity of binary search. What is the time complexity of binary search? I mean, have you heard about binary search? Most of the students here.
It's log n.
So, yeah, fine. Like what log n? Is it theta of log n, O of log n, omega of log n?
Oh,
O of log
should
n.
be.
O of log n.
Of,
Is it
yeah.
theta of log n? Is it theta of log n?
No,
Why not?
because the program could terminate in the very first step itself.
Exactly. So you can say time taken for binary search is O of log n, or you can say time taken for worst case of binary search. That means you have already limited the data distribution of this, then it is theta of log n. Or you can say, I mean, this is same as
I see.
saying worst case time complexity of BS is theta of log n. Make sense?
Yeah.
Whenever we just say code segment, we are not considering, I mean, it depends. I mean, some people might say by default worst case complexity and all, but ideally we should consider all cases. Okay, all
So the
cases.
yeah, so the worst case is a subset of all cases, right?
Worst case is a subset of all cases. For example, best case time complexity is theta 1. Yeah, you can write something like this. There is no problem. But what is the complexity of binary search in general? It's not theta 1. It's not theta log n. It's, I mean, it includes everything. Hence, we write it as O of log n. Make sense?
Yeah.
Okay, let's move on. Right. Okay, so we will have to go at a faster pace. We have a lot of material to cover. Loops. Suppose we have two loops, right? One for loop, another for loop, and then block B. And suppose this is independent. I mean, suppose this is constant, right? I mean, independent of all this ij and all that. Okay, then you can write it as mn, the number of times this the loops will run, times time taken for b. Maybe it is theta of p cube or something like that for some parameter. Okay, this is simple. Next, suppose you have this. How do you find the complexity of this code? Sigma I is equal to 1 to m. Sigma j is equal to 1 to n for the loops. See, for every loop, you can write it like this. I mean, in fact, you can also write it like this. Sigma I is equal to 1, m, j is equal to 1, n, time of b is equal to, time of b is independent of I and j. So time of b, sigma, double sigma, m times n times 1 is equal to mn time of b. That's what is written here after simplification.
Professor, a really
Yes.
fast question, really
Yes.
fast. I know we have a lot to do.
Yes.
For the loops, if J is not independent of I, is it still M times N?
Where in the second problem?
No, in the first one, not in functions, in loops. Say J goes from 1 to I. So it's dependent on I. Do you still multiply the two sigmas?
So I mean, like, we are not multiplying the two sigmas, right? So for this example, we are doing it, right? But if it is dependent on this, I mean, so you can always pull this out if it is independent of I and j, right?
Yes.
Suppose time of b is p cube. Pull it out, right?
Yes.
Okay, then it is 1. J is equal to 1 to I. Then you need to solve this first sigma, right? Get a proper expression and solve that second sigma. This expression will be a function of I.
Okay, got it. Got
Right?
it. Yes.
So
Okay, thank you.
you solve the innermost expression first and, you know, keep on
Yep.
going to the outer layers.
Yeah, I got it. Okay, thank you.
Right. So here, see, this function is dependent on ij. So you cannot write it as f of, you know, m comma n times mn. No. Right? Solve this problem. Suppose f of ij takes theta of ij time. What is the complexity? Right? So see, I can ask any questions like this, right? Given a program segment, what is the complexity of this? And the more functions it has, the more constraint it has, the more complicated it will be, right? So you might have seen from the homework, right? Even 2-line code analysis is so complicated. Now think about thousands of lines that you write. Okay. Anyway, let's move further. So here are a couple of important links. Go over, I mean, you can click on this. It will take you to Wikipedia pages. You need to know some of these, right? The basic differentiation rules, the basic derivatives, basic integrals, what is integral of log, what is integral of a polynomial, some series, right? All these things. See, whenever we studied mathematics, we were asking these questions, right? Where in the world we will use all this? So did you ever think that in programming, right, in complexity analysis, makes heavy use of calculus, limits, integration, differentiation, limits, right? Series, infinite series. We feel like infinite series is out of earth, right? Nobody knows, how to use it properly in real life, real world situations. But see, it comes extensively in analysis of algorithms. Okay, and we have solved a couple of problems here. So try to solve the remaining. And how do you prove, something like this? The way you need to prove is prove this one and prove this one. Oh, sorry, this one. So take two at a time, two adjacent at a time, right? Or you can also show that this is equivalent to 1, because you have kind of equal to sign everywhere, right? A is equal to B is equal to C is same as A is equal to C, right? So there are multiple ways of showing this. But whenever you have less than, you need to show that, so consider these two functions and show this function f is less than g. Then this g is same as h. H is less than something else, p, right? So on. So one line like this, it includes probably how many? The number of proofs you need to write is same as the number of functions minus 1 here, right? Okay. We have scanned all this. Okay, let's move to this important problem. Log of n factorial. It is same as theta of n log n. Whenever you see log of n factorial, write it as theta of n log n. And how can we prove this? Let's see. Log of n factorial. N factorial is n times n minus 1 times so on up till 1, right? So what you can write is log of AB is same as log A plus log B, right? So suppose we write this as log n plus log n minus 1 plus log n minus 2, so on up till 1. Okay. And that sum is less than sigma log I, and it goes to infinity. You're not just taking till n, suppose you take to infinity.
Quick question.
Yes.
But we're already saying that n is going to infinity. So what difference does it make having that as explicitly infinity as opposed to just keeping that as
Oh,
n?
good question. So because if we have infinity here, we can directly substitute the formula of this infinite series.
Oh,
But
as an
this
integral.
infinity will be processed much later after a lot of cancellations, right? So that we cannot exploit n further.
I see. Okay.
Make sense?
Yeah.
Okay. Now this, we can write it as convert it to ln. When you convert it to ln, you get some constant outside. Okay. Now there is a formula for this sigma ln I is too difficult to find, right? In fact, sigma, many functions like this are too difficult to find. So there is no proper formula that can solve that problem. So whenever you have sigma of a function from I is equal to 1 to n, you can write it as sigma I is equal to 1 to infinity f, right? That you can say approximately equals integral of f from 1 to infinity. So this is beautiful, right? So you can approximate it as an integral. See, this n, upper limit n is less than or equal to infinity. For most, positive, you need to think about the some functions. For some functions, it might not be true, right? So you need to think about what kind of function it is, right? And then this is approximately equal to integral. Okay, that same idea we are using here. And for integral, we have formulas. So this integral is same as x ln x minus x plus c for some constant. And we don't care about this constant. We don't know the constant. We don't care because we can just substitute 1 to n here. Right? Okay. Next, solve all this problem. This is now basic substitution, right? You get this n ln n minus n. You have n log n. So you can take all this common factor out and all, right?
Professor,
Yes.
the integral we did is from 1 to infinity, yet we are substituting n.
Okay, so
we-
probably
So we ditched n by saying it is less than and replace it with infinity, and then again in the limits we are substituting n.
you are right. I think, okay, let's think about this. Okay, so we don't need infinity here. We can keep n always. See? We can keep n always.
Okay.
Right?
Yeah.
That is still the same. Because ln x is a function, and integration, whether we don't need up till infinity. We don't need this infinite series. Right? We can stop it at n. And
Okay.
we are having these lower and upper bounds from 1 to n, right?
Right.
Okay, so these mistakes I'll fix it.
Also, if you're gonna switch that back to n, then that less than sign.
Right.
Equal,
This will be normal equal to, right? Then there is no problem. You're right. So we don't need infinity here. Okay. So and here also, so verify, right? Sometimes the point is this: in CS we use log base 2 a lot. In math we use log base e a lot. I mean, we write that as ln function, right? Log base e is ln. So whenever we want to convert from CS to and integration and all is defined for ln, right? For log base e. So every time we need to convert this base from 2 to e, process it in the math world, right? Using this integration, difference, whatever, and come back to the CS world, right? So that so in that conversion, right, we might make some errors. So please be careful, if this is being right or not. So here I used log, here I'm using ln. So maybe there might be a mistake. But it's a constant, it doesn't matter. We don't need the number here. We just need to make sure that it's a constant greater than 0. That's it, right? But still, to be correct, right, we want to properly convert between this base 2 to e, right? So verify all these things, right? There might be mistakes, but you get the overall idea. Got it? And we should be very careful whenever we are converting, right? There can be mistakes in the conversion, but make sure at a high level, the core logic is 100% correct. Next, I think we scanned some of these, right? Okay, now consider this. Log n is asymptotically less than log n. So how can we solve this problem? Log n. and log n. See, if you directly substitute n is equal to infinity, we get infinity by infinity, right? So it doesn't work. So what we do is we use L'Hopital's rule. So limit f divided by g is same as limit f dash divided by g dash. I mean, that was the idea, right? If the limit exists, if the denominator is non-zero, and so on. And if the style is like 0 by 0 or infinity by infinity, we can apply L'Hopital's rule. And
Professor,
yes.
I think generally the methodology has no problem. However, we need to point out that the L'Hopital's rule applies for the continuous function. Here you use discrete function, right? So we probably cannot apply it directly.
No, true. But the concept of limits, right?
Yeah, that's no problem. I'm not questioning that. I'm saying, so maybe we need to point out this applies, say the n is not the n. Let's say it's x, right? It's log x. So x is continuous. And of course, when n goes to infinity, there is no much difference. But mathematically, I think that's more I think more generic, I think.
True. I mean, that is true. Here, n is not, n only takes natural numbers, right? In computer science.
Yes, it's great.
But the
right?
theory of math for continuous functions can be applied for this to show all that asymptotics,
Yes.
right? So you can assume that these are continuous functions because the math works out. Finally,
Yes.
whatever you get, the complexities will remain the same. So here we don't need to show, if this is continuous function or not. It doesn't matter. Assume that all these are continuous functions because that was the definition of it, right? They use limits to prove all this, relationships. I mean, they defined it in that way, right? But you're right.
I think if we add one more step here, just underneath the first line, let's say limit n goes to infinity. Let's do an exchange. Let's say n, make n x a positive number goes to infinity, but it's a real number, not an integer. I think that probably make it more formal, kind of mathematically formal.
Right. I mean, you can write it as x, but it doesn't matter. I mean, we are only focusing on programs here, right? Hence, we are using n. But you can assume n as continuous only. The math works out, right? We don't need to change this, right? Because whenever we write it as, the complexity of this algorithm A is theta of n squared only. And we are comparing those functions, right? I mean, that's fine, right? Do not worry about that. So, okay. So when you take the L'Hopital's rule, you take the differential of the first function and the differential of the second function and convert it to required the base and all, right? And you see that n cancels out. You get this of the form 1 by ln n, which is 0, right? See, L'Hopital's rule is a very powerful idea. So whenever if you directly substitute, it is of the form infinity by infinity or 0 by 0, right? If the limit exists, you can use L'Hopital's rule to solve your problem. Okay, and know a lot of rules related to logarithms, some basic algebra powers, right? A power x times b power x, right? Or a power x times a power y, and all these rules of algebra, right? They will be extremely useful, all these things. Okay, so I have just given some basic derivations. Try to solve all these problems. Okay, all these problems and also problems from your homework. Okay, fine. I think we are done with analysis of algorithms. That's it. We covered this. So try to write the remaining complexity analysis. And this is given in your homework also. Okay, let's move to arrays and lists. So practice analysis of algorithms a lot. It is complicated, right? Whether analyzing a code segment for complexity or trying to compare two functions which is smaller than the other, or if they are equal, right? Asymptotically, that's complicated, right? And there are multiple ways to solve the problem. So just because I showed one approach, it doesn't mean that's the only approach. There are many ways to solve the problem. So any approach that is correct, right, is acceptable. Okay. But for comparing, as you have seen, we heavily used limit approach. We didn't use set approach because it will be extremely complicated if you use set approach. So use limit approach whenever possible, okay, to compare two functions. And to find the complexity analysis, we heavily use sigma notation, right? If you remember the analysis of kernels and all, right? We use sigma notation a lot. And whenever you use sigma notation, you might have to use infinite series. So try to learn all these things. What is sigma I? What is sigma I squared? What is sigma I cubed? What is sigma log I? What is sigma 1 by log I? What is sigma? So like these, right? So try to learn all the summation of all these infinite series and all that. Okay. Fine. Let's move to arrays and lists, and we will increase the pace. Okay. Okay, you might have coded a lot of programs that had used either arrays, vectors, strings, tuples, lists, sets, and so on, right? What are the differences? Different programming languages have different names also. One uses array, another uses something called vectors. In C++, you have vectors. And in Java, you have something called array list. In Python, you might have list. And there is also set, tree set, and then string. What are the differences between all these? Are there any differences? What's the difference in the performance? What is the difference in how they are stored, how they are accessed? What are the differences in their functionalities? For which functionalities, which data structure you have to use, right? It's not very clear, right? So here we will see the underlying ideas, algorithmic ideas and insights behind all this. Okay. So here we will go for linear data structures. These are called linear data structures. For a couple of sessions, not only this, even stack, queue, dequeue, all those are linear data structures. The first part will be majorly looking at linear data structures. Okay, let's start with arrays. Then we will go to SLL, singly linked list, CLL, circularly linked list, doubly linked list, DLL, right? And then abstract data types such as array lists and positional lists, so on. At the end of this, you should know a lot of ideas related to arrays and lists and which one you have to use for which applications and so on. Let's start with arrays. So here is a simple game scoreboard. Okay, so one more suggestion, right? From, if you are not already doing it, so try to look at the previous lectures, right? Either recorded lectures or all the slides and the related topics. Study all these before coming to the class, because we will be looking at a lot of codes and I don't want to spend time on explaining each line of code. It's majorly waste of time, right? What we have to focus on are the underlying algorithmic ideas, insights, analysis, and discussions, right? How we can apply it to real programs and so on, right? Hence, if you can study a lot of these material before coming to the class, you already know the slides, you already know the exact chapters in different books that you need to study, right? if you come here prepared, it will be so helpful. We can skip all the unnecessary details related to coding. We can focus on algorithms, right? Deeper ideas, mathematics of it. Okay, storing game entries in an array. So here is a simple application. Suppose you want to save top 10 game entries in a game. Top 10 highest scorers, maybe in the FIFA Cup or in car racing or whatever. And so if you look at this, this is an array, right? Array of entries, and each entry can be considered as a structure. You have names, you have scores, and if you look at a higher level picture, these scores are in descending order, right? Descending order from left to right, descending order. Highest, second highest, third highest, so on. If another person comes who has a score of 700, right? That person has to be put here, because after adding that number, the final array should be in descending order. So this is the invariant. What do you mean by an invariant? It is a property of a data structure, algorithm, procedure, whatever, that does not vary, right, after a particular operation is applied. See, after insertion, it is still in descending order. After deletion, suppose you deleted, say, Rob's entry, the final data structure should still be in descending order. So it is an invariant. Okay, anyway, let's proceed. So here we have game entry, public class game entry for each entry. Okay, for each entry like this, we have game entry. So there are multiple entries that make the scoreboard, right? But we are talking about one entry now, game entry. So you have name, you have score, and you have a constructor, get name, get score, toString, right? We don't need to worry about the details. That's the high level idea. Okay, easy. Next. Scoreboard. Now we are talking about the board itself. And you know, there were top 10 scores, but maybe you can change the capacity also. Need not be top 10, it might be top 50, whatever. Okay, so we have a class scoreboard, and you have number of entries, and then you have the array board. Okay, you have the constructor where you define the capacity and you create that array. This is the array. And what are the functions you want here? You want to add an entry, you want to remove a particular entry. That's it, right? Add an entry, remove. In most cases, it will be add and remove. And in some cases, you might have add, remove, search. Okay. But here we are not searching, add, remove. Okay, adding an entry. The idea is simple. Whenever you add an entry, after this operation, it has to be in the descending order only. So what you do is you find, suppose you're adding this entry, Jill's score is 740, right? Find the correct position where this can be inserted, right? So it's here. And find all the entries that have scores less than 740 and push them one step to the right. One step to the right, so that you make room for the new entry and add this new entry here, wherever there is empty spot. Now think about it. You are trying to find a location where that entry has to go to. If the entry goes to the last position only, right, then the number of these movements will be minimum. But suppose you are adding one entry, say John, with say 10,000 points, where will that go? It will go here. That means all these entries should go towards their right positions by 1 unit. Now look at the time complexity. If it goes here, every element has to shift by 1 unit. So in the worst case, the time taken can be n. The worst case is n. So let's say theta of n in the worst case. The best case is theta of 1. So the overall complexity is O of n, right? So hold on to that idea. Now let's see how this works. Add. So check whether if this is a news code. If it is a news code, see the core logic is here. The core logic is here. So find the you want to find the correct position, right? Where that entry can go. So you start with the last entry and keep checking whether it is a smaller number than the number you want to add. If it is a smaller number, keep shifting right. So this is shifting right, keep shifting right. So keep doing this in a loop until no number is less than the new number that you are adding. That means that then you have found the correct position. Add that entry into the correct position. Done. Simple. Make sense? Okay, so as you see here, what is the complexity of this add operation? It depends on while. This while. See, you don't need to care about each and every line here. All these are constants, right? You need to focus on the big things that eat the time of your course. And that is this while loop. How many times does this while loop run? The best case can be 1. The worst case can be the total number of entries, right? So that's it. It is O of number of entries. Let's say the number of entries is n, it's O of n time complexity. That's it. That's how you analyze the time complexity. Okay, next. Add is done. How do you remove an entry? A very similar approach. You can say it is the reverse approach of adding. See, suppose you want to delete this entry, Paul 720. What do? Delete this entry and shift all the elements to the right by 1 position to the left. Suppose you want to delete Mike. Delete this entry and shift all the elements to 1 position right. Right? In the worst case, what happens? In the worst case, time complexity is n. In the best case, if you're deleting the last entry, no problem. It's just 1. Okay. So that's the logic. See, here you're removing an entry at position I. So you check all the elements from position I to the last position and keep shifting them by 1 unit to the left, j plus 1 to j, that is 1 unit to the left. And at the end, the last entry will be empty, right? I mean, you don't want to use it. It's better to replace that with null. See, many people don't do this. Line 8. Can you tell me why we should do this?
Because then if you do a 2 string, the last entry is going to show up twice.
No, suppose you are, like if you decrement the number of entries and just print the number of entries, then it will not show
I
up.
see what you're saying. Not saying, well, you have, it's just not good practice to leave something in memory in an array that you're not going to use that really shouldn't be there. Because that person,
Exactly. Exactly. The correctness will not change. Okay. It is still a correct program. There is no problem with it. And if you want to print the exact number of entries, you can. There is a way to print exact number of entries. There is also no problem with that. The problem is in the art of programming here. When you are 100% sure that you won't be using that object, right? See, this points to an object. And that object is just a tiny entry here, but in real life, real world, that entry can be a 100 or say 1 GB object. It can be, right? Just, ignoring it, you're holding all this space, right? That some other processes could have used all these. Hence, you want to make sure that if you are not using this object, set that to null. See, when you set that to null, you're not deleting this object from the memory. Are you deleting this object from the memory? No. That object is still there. Can you tell me what happens then?
The array position just isn't pointing to it anymore.
Right. Array is not pointing to it, but you still did not delete this object, right? So it is still holding some space. What happens then? Okay, so see, null, okay, you understand this. From here, we are not pointing to this object. Whenever from your program, you are not accessing a block of space, the Java programming language will assume that this has been released to its environment and it can use it to any other, processes. So the Java garbage collection, right? Garbage collector. So that program will assume that, okay, now this object is not accessible from, your program, right? Once you do this, you lost your pointer to this object. You cannot access this object at all. Once you have lost your pointer, Java assumes that that object has been given to garbage collector. So later, when the garbage collection algorithm runs, it will clean up all this space and give it to more, programs if necessary, right? So you don't need to worry about deleting this. In C and C++ programming language, we used to delete all this, right? That is not required in Java and probably advanced programming languages. You just set it to null. The programming language will take care of cleaning all this object, right? And giving that to, some other processes, okay? ToString is about just printing the board. We will not go over this one. So main function. What's the main function here? You have a list of names, you have a list of scores, and you create this game entry for particular name and score, and keep adding them here, right? Now you have a big score, and you delete some of the entries and see what happens to that board. Okay, you can try doing this. But anyway, we don't care about this. Now you understand how add works, right? Add function works. You understand how remove function works. Given the constraint that the array should always be in the sorted order, right? This is exactly the logic behind insertion sort. So if you have played card games, suppose you want to sort card games. You got a new card. Suppose you took a new card from the pack. Where will you place it? You automatically place this new card into its sorted position, right? To do that, from your fingers, you try to push all these cards that are, say, larger than this number 2 one step to right. You make some space here and you put this card into its correct position. Isn't this the exact logic you used for inserting game entry? And similarly, deleting. How does deleting work? Suppose the card 3 is here. You are removing this card. You have extra space here. All these cards will take up the previous positions, right? One space to the left. The exact same logic that you used in the remove function of scoreboard application, right? So if you understand this add and remove, add, you have understood another sorting algorithm, insertion sort. Okay, I will not go over all the details. You can learn this on your own, right? So the idea is simple. You have an unsorted array and you start from the second element. So suppose this step 1 is working on the second element, step 2 is working on the third element, and so on. There are so many steps. In step 1, you try to find the correct position for this 3. Right? So after each step, the elements that you have checked till that point is in the sorted order. Right? Okay, now consider, suppose suppose consider this one. So before this step, step I, all these elements are in the sorted order. And now you consider the next element 5, find the proper position for 5, shift all the elements that are larger than 5 to right by 1 position, and place 5 here. That's done. So after step I, the array that you have seen till that point is sorted. So, right, this is sorted. The partial array before step I was sorted. The partial array after step I is sorted. That means before step I minus 1 elements were sorted. After step I elements are sorted. The first I elements are sorted. After step I plus 1, the first I plus 1 elements are sorted. And this is the exact logic from your playing cards or the add function we have seen till now. Right? So using that, you can also get this insertion sort algorithm. Okay, so go over this logic. I mean, we have covered the basic way it works. Go over each and every line, right, and code it also. Okay, I think we will stop here. I will not go over all these slides. There is some slides on random numbers, some slides on 2D arrays. They are very basic examples, right? Go over these, how you work on 2D arrays, and that's it. And from next class onwards, right, we will start with this complexity analysis of arrays, and then we will go to lists. Okay. So at this point, we'll stop.
Thank you.